ACT12, what we're doing is we're looking at how particles that are two different sizes, about 2 orders of magnitude different, with very different charges on them, will aggregate and hopefully crystallize in a microgravity environment. The nanoparticle haloing refers to the fact that we have small particles that are very highly charged that basically protect the large particles which are uncharged. And this allows our system to be much more stabilized and have long-term stability. Eventually gravity does win out on ground, and that's where we get that densification and that crystal structure forming. But with the nanoparticle haloing, that allows us to get a crystal structure as just opposed to a hodgepodge of particles falling in whatever order they're going to fall in. The small particle in this case is important for what we want to do technologically, because it's that small particle that we can then use to actually tweak the properties of the crystal, whether that be to allow them to absorb certain wavelengths of light, or even allow us to maybe reflect or deflect light in different directions. With optical computing, one of the key issues that you run into is you have to be able to switch light, whether that be you're switching light from one fiber optic to another, or even if you're trying to play with bits. If you have just a single crystal material, you have no way of switching. By adding in that second particle, though, that's what actually gives you the capability of now being able to do things like diffract light through the crystal so you can actually get light bending, or being able to segment light so that you can maybe tune it so you can get your 1-0 type bits. The microgravity environment is important because when we look at these types of systems aggregating in a gravity environment, what tends to happen is the larger particles will artificially densify as they drop to whatever base you have and push out the small particles. So when I do get a crystal to finally form, I'm only getting a crystal structure of that large particle. The small particles tend to stay in suspension. Over the last couple of years, people have started looking at originally dye-sensitized solar cells, and now they've moved into quantum dot sensitized solar cells. And one of the major issues that you have with these types of solar cells is they will blend a charge-carrying particle, which is usually something like titanium or tin oxide, with a quantum dot material that could be cadmium selenide, lead sulfide, something of those natures. When they do this, they just kind of mix them and then they put them on a surface, and hopefully they get something that resembles a nice structure. But because they're not pre-planning this, the structure that they ultimately end up with is somewhat haphazard, which leads to a lot of inefficiencies within the solar cell itself. What we're hoping to do is utilize the nanoparticle haloing mechanism to create a nice structure of the nanoparticles around our charge-carrying particles, and then we crystallize both of those together, so now you have a crystal structure within a crystal structure in essence, which then allows you to produce charge much more efficiently, hopefully giving us as efficient a solar cell as we can possibly get. The advantage that we get with using maybe a quantum dot sensitized solar cell is that they're much cheaper to produce because you're using much cheaper materials. And additionally, if you can use a polymer electrolyte, you can actually get them to the point where you can roll them up and ship them as a roll, as opposed to having to ship them as an entire panel, saving a whole lot of space as you go up into space. At this moment, we're not sending up the true quantum dot sensitized solar cell system, partially because it's a little bit more difficult to generate. So what we're starting with is sort of an analog system where we're using a large particle that is very like silica and a smaller particle which is readily available in zirconia. These particles are very easy to modify, they're very easy to deal with in solution phases. We don't need to go to high pHs or very low pHs. They're very easy to suspend within an aqueous system. And so this allows us to really look at the fundamentals of nanoparticle haloing and how that crystallization can occur, so then we can then transfer that knowledge to the actual quantum dot-based systems. One of the systems that we have at the University of Louisville is a roll-to-roll printing technology where we take films of polymer and we can print directly on those polymer films. And this is basically the half step to full-on production capability that you would see in any industry that you're kind of working with. And then you'd be able to roll it up because, again, it is a roll-to-roll printing, so you'd actually roll it up at the back end and you'd have a rolled-up solar cell that you could then sell as product. NASA Glenn Research Center has been key throughout this entire process, because while we have a general idea of the experiments we want to perform, how they need to be performed in space and what the actual experimental constraints are something that you really can't plan for until you actually come and talk to the people here. In addition, you're really looking at how you can extend the science beyond what you've originally planned for, and that's really key because the people here know what's going on the space station, they know what the instruments are capable of, and they know how they can push the instruments into new directions, and that's been really key for us.